I want to talk about future prospects for Parton showers. I think everybody knows that Parton shower event generators are important phenomenologically, but what I want to talk about here is the theory that goes into them and what's the prospects for improving the theory. There's a draft white paper with lots of references, and it's just not possible to include references in this short of talk, so I'll just leave those out. So let me just briefly review what Parton showers do. Here's a cross-section or something you'd like to see, a jet cross-section, let us say. And the way you get that is you convolve Parton distributions with a hard scattering cross-section. So the idea of a Parton shower is it's a approximate calculation of this hard scattering cross-section at a very high order, but completely approximately, just based on the singularities of QCD. And the way it does that is it uses the renormalization group. So you can imagine here a hard scattering at a 1 TeV scale, quark-quark scattering. However, if you go now to a smaller scale, 500 GeV, then maybe one of the incoming quarks emitted a gluon. And if you go to yet a smaller scale, maybe one of the outgoing quarks emitted a gluon. And at smaller and smaller scales, there's more and more emissions, and that's what you call a Parton shower. And that's the way that these Parton shower event generators work. So what issues are there? First of all, there is matching. If you have the Born matrix elements to start with, that was this very hardest thing, then the shower will generate approximate corrections of order alpha strong squared, etc. But those are approximate. And suppose that you have exact perturbative corrections for a particular hard scattering cross-section, let's say a jet production, at order alpha s or even 2 orders of alpha s. If you have those exactly, then the shower is doing it wrong, and you have to get rid of the shower approximation for those first 2 orders and put in the exact calculation. And that's what you call matching. And we had a nice talk just this morning by Marius Wiesemann of how that works. It's very important, and it's been the subject of a very large effort in recent years, and that effort is continuing. And there's a related topic or issue, merging. That's where you try to match the 2 processes at once. So proton-proton goes to Higgs plus anything, or proton-proton goes to Higgs plus 1 jet plus anything. And evidently, well, that's called merging. And merging evidently requires definitions to differentiate those 2 processes. So there's some ambiguity that you just have to settle. Again, there's a lot of work that's gone into this, and work continues in that area. Okay, let me talk just a moment about quantum interference. The Parton showers need to follow quantum mechanics. So typically, the modern ones explicitly include quantum interference. So I've drawn here a picture of an amplitude squared. This is an amplitude, that's a conjugate amplitude, and I just squared the amplitude. So in the very earliest days, that's what you had, the amplitude squared. But there's interference diagrams, and those are included now, typically in Parton shower event generators. So here I emit a gluon from gluon 1, and I have the interference with emitting that from gluon 2. And that's the name of that kind of shower is a dipole shower. So now we have quantum interference in our shower. But let me talk about spin. Partons carry spin, and that's a quantum variable. So to account for that, you need the evolution of the spin density matrix, just like you'd use for photons, for polarized photons. So that's a ket spin state and a bras spin state. And to include those, there's a nice algorithm that's due to Collins and Knowles. And most of the Parton shower event generators do not include that, but they should. It is implemented in the latest version of Herwig. And there's further work to be done to just include it. But I think work like that is progressing. And I think before the next Snowmass, though, everybody will have that. Okay, color. Partons carry quantum color. And you need to account for the evolution of the color density matrix. State of, say, 20 partons, the color state of 20 partons, and the conjugate color state of 20 partons, which is typically a different color state. So that's actually a very difficult problem, and most programs use what's called a leading color approximation. It's the leading term in an expansion in 1 over the number of colors squared. But there's been extensive recent work just in the last few years that studies the color density matrix evolution resulting from both real emission graphs and virtual exchange graphs that affect the color states. And I can add a personal note. My choice is to use the LC plus approximation, which Zoltan Neitsch and I have worked out. That's quite useful. I think other programs ought to use that. But it's still, there's lots more to be done. And you need to have not only the leading approximation, but corrections to the leading approximation so you can tell how good your approximation is. Okay, large logarithms. Many important cross-sections depend on two very different momentum scales, like the W Brilliant production and then transverse momentum of those W's, which can be very different. So your cross-section then contains logarithms, say call L, of the ratio of your two scales, the PT and the W mass in this case. And you want to sum terms of the form alpha S to some power and log to some other power for at least the biggest powers of logs. So there's a huge industry to develop analytical formulas for summing large logarithms of whatever particular sort you have in mind. But a Parton shower event generator contains the singularities of QCD, the infrared singularities. So the Parton shower has a chance to get those large logarithms, and in some cases it does a good job with that. So it's a tricky issue, actually, to see how good a job it does. And that issue is a subject of intense current study, and it will be in the next few years. You'll hear more about that. Included under large logarithms are threshold logarithms. Those have been known for a long time. They're important when Parton momentum fractions are large. And there's a large literature of analytical formulas for summing the threshold logs. One Parton shower algorithm sums it, but mostly the Parton shower algorithms don't sum those. However, going back to matching, if you match to next to leading order or next to leading order perturbative calculations, then you include a lot of the threshold logarithm. So that can be a big help. Okay. Let me mention electroweak radiation. And mostly what we've covered in Parton showers is QCD, but you can also have electroweak bosons emitted, and you could also start then with electrons instead of hadrons. So for the LHC and future colliders, it would be good to include electroweak radiation in a Parton shower. And that's a challenge. The nature of the theory changes between very large scales, much above the W and Z mass, and smaller scales, because the SC2 gauge theory is spontaneously broken. So it's just nature changes. And you have to account for that. You have to match that. And furthermore, protons and electrons are not singlets under the SC2 cross U1 gauge group, whereas they are singlets under the SC3 color gauge group. That makes it much simpler. So there has been substantial work to address these issues, and that more work will be done in the next few years, I think. And let me close with a mention of next to leading order shower, and then we can do questions. So the Parton splitting operators in current Parton showers are all of order alpha S. That is, say, one gluon turns into two gluons, or you exchange one gluon. So that's pretty limiting to be just that order of perturbation theory. And it's an important goal to construct a Parton shower with splitting operators at order alpha S squared. However, that's really tricky and nobody has done it. It's roughly equivalent to constructing the infrared subtractions for next to leading order perturbative calculations with color in both the initial and final states. And that has been done now for perturbative calculations, but it took a long time to do that. So similarly, it'd be really good to do next to leading order Parton showers, which is kind of equivalent to that. And that's a goal for the future, but there has been recent progress in this direction and people are continuing to work on it. Okay, that was my last slide and I can take some questions.
Thank you very much, Dave. Thanks for this nice talk. Okay, questions from the room? Do we have questions from Zoom? Nathaniel.
Great, thanks Dave for a great talk. This is Nathaniel Craig. Just a quick question. So you mentioned indeed progress in incorporating electroweak physics into the Parton shower. Can you just say a little bit more about electric radiation, where things are, what the near-term prospects are?
Yes, there's been work both on just the showers and also work on the Parton distribution functions that you need for those. So it's in a kind of early stage now. However, Herwig has an Electroweak shower built into it now. I mean, not completely everything you'd like, but something that's very nice. And I think it's particularly important if you think about future colliders. But the Herwig people found that it makes a difference even for the LHC because there's large logarithms associated with emitting electroweak bosons, and it helps to include that in your shower. Does that help you?
Yes, thanks very much. Obviously, it's something we're worrying about for muon colliders, but interesting to know both.
Yes, for muon colliders, it's important.
But also interesting to know that it's also relevant now for the LHC. Thanks.
I have a quick question, Dave. So, yes. Do we have a good theoretical understanding of what observables a Parton shower contributes to at the level of next leading log resummation?
Yes, that comes under large logarithms, and there's been a whole lot of work about that. What you can do most successfully for electron-positron annihilation, where the theory part is a little easier, is analyze either analytically or numerically by very clever numerical methods how well your Parton shower is doing. So I might mention I have alpha s to the n log to the m. M, if we're talking about the cross-section, m at max is 2 times n. So that's a lot of logs. However, it typically organizes itself into the exponential of another series in which alpha s to the n multiplies log to the m, and m at most is n plus 1. And the logs with n plus 1 are called leading logs, and logs with m equals n are called next to leading logs. And if you're clever about it, if you're clever about it, you can sum at the next to leading log level. But it takes putting a little more into your Parton shower than you just get out by matching the singularities of QCD. In particular, in the splitting functions, the alpha s that you put in there should be alpha s evaluated at a scale kt squared instead of whatever scale you're using in the shower. When you do that, then you can get next leading log summation for a lot of variables, and people just test for this variable, that variable, another variable. And if it's working out, then they're happy. However, when you do that, what you notice is if you vary some things in the Parton shower algorithm that seem kind of minor, like when there's something called momentum mapping. In order to conserve momentum in your shower, you need to take some momentum from someplace and put it into the splitting. You change the momentum mapping, and that can change how well you're summing the logarithm. So it's a fairly tricky business, and it's not exactly obvious, but it's the subject of lots of work.
Thank you, Dave. And just a quick question. You mentioned that there is some effort to go beyond the leading color approximation, and you refer to the LC+. I don't know exactly what the LC+, what details go in there, but I'm curious, what's the difference between LC+ and LC in terms of
Oh, yes,
data?
I can tell you that. Where did I put it here? LC+ is in the Parton shower resultant Neuschenme. What it is if you exchange a gluon between two partons, then you leave the number of partons the same, but you change the color state, either the C state or the C prime state. So now it's tricky to include that change in color because exchanging gluons between two partons gives you an operator that you'd like to have the exponential of that operator because you have the exponential of the probability not to split. So exponentiating a matrix in the color space that's 10 to the 25 dimensions is evidently impossible on a real computer, even on a quantum computer, I think. So you need to do something. And the LC+ approximation leaves out some of the contributions. It leaves out the contributions that you can't deal with, but includes a lot of other contributions. And then it turns out that the matrix that you want to diagonalize is diagonal in color. So then you can exponentiate it. And furthermore, if you have the splitting function minus the LC+ approximation, you can call that delta splitting function, you can include powers of delta splitting function, as many as you like, and see how well the approximations work by expanding in the difference. Well, you cannot expand in to 10th power, but you can do 2 powers, and you can then test how good that approximation is. So to my mind, that's the way to go, but there are other people who have different ways of dealing with it, and we'll have to see. It's a matter of current work, and we'll have to see what works best. But certainly, people should take it seriously, to my opinion, and they should always talk about how does the color density matrix evolve, because I think that's the only way to really keep track of color.
Thank you very much, Dave, for all these answers. And thank you to all the speakers of this afternoon. So let's give them one more applause. And then we have the coffee break.